Now that we know where energy comes from and how it's used by organisms, is energy shared equally between organisms? The answer, if we think back to the second law of thermodynamics, is obviously no. We can think of energy as flowing through an ecosystem, starting at the sun, then being absorbed and converted to sugar by plants, and the plant's energy is then consumed by a heterotroph, and that heterotroph is then eaten by another, and so on. We can illustrate energy flow in an ecosystem by drawing a food chain or food web. Each level of a food chain consumes the one before it. In this food chain, we have a plant that consumes the sun's energy, and we have a mouse that consumes the plant, the snake that consumes the mouse, and a hawk that consumes the snake. Each of these levels of the food chain is called a trophic level. The first trophic level is always an autotroph. Animals make up the other three trophic levels. The second level is typically an herbivore, an animal that consumes plants. The other two trophic levels consist of predators that eat other animals and/or omnivores that eat plants and animals. At all trophic levels, there are also detritivores, animals that eat dead material, as well as decomposers, typically fungi and bacteria that break down dead and decaying organic material. The number of trophic levels and the number of individuals at that trophic level is determined by the second law of thermodynamics. Every time an organism is consumed, some of that energy is lost as heat. The higher your trophic level, or in other words, the further away you are from the sun's energy, the less energy you have available to you. If you notice, as the sun's energy is transferred between each level, some is lost as heat. Therefore, the hawk has much less energy available to it than the mouse. We can also visualize this as a pyramid. Most of the energy on the planet is trapped in plant biomass, or plant stuff. Primary consumers, the herbivores, can only utilize around 10% of plant stuff. Secondary consumers, the predators of the herbivores, only have access to around 10% of the energy from consuming the herbivore. Tertiary consumers only have access to 10% of the energy from consuming the secondary consumer. From the perspective of the plant energy, secondary consumers receive around 1% of that energy, and tertiary consumers receive only around 0.1% of that energy. This loss of energy at higher trophic levels cap both the number of trophic levels to 3 and greatly reduce the potential population size of top consumers. There are a lot more mice than hawks. I hope that this is quickly becoming apparent that energy availability is important for ecosystem function and composition. On top of all of this, not all ecosystems produce the same amount of energy from the sun. Indeed, there are many ecosystems that produce a lot of energy, like rainforests and coral reefs, and some that produce very little, like tundra and deserts. We measure the productivity of ecosystems by measuring what is called gross primary productivity, or GPP, and net primary productivity, or NPP. GPP is the total amount of energy that plants capture and assimilate from the sun during a given time frame. However, plants also require energy to survive, so NPP is GPP minus cellular respiration, or R. NPP is what's available for all other organisms as food. How is this important for environmental science? Well, humans consume around 30% of global NPP, but only make up about 0.5% of the global biomass. I want you to think about what the implications of this is and how this could impact the environment.